and welcome to the first video of the ISTQB Certified Tester Foundation Level Preparation course. My name is Dmitry, and I'm a Creative Manager at Exactpro. Today, we will cover Chapter 1, Fundamentals of Testing. Most people these days have had an experience with software that did not work as expected. A delay when waiting for a credit card to process, or a website not loading correctly are common examples of that. Some of the system failures we encounter are quite trivial, but others can be costly and damaging, and may even result in injury or death. Testing is a way to assess the quality of the software and to reduce the risk of software failures in operation. The quality is the degree to which a component or system satisfied the stated and implied needs of its various stakeholders. One of the commonest misconceptions about testing is that it's just activity during which we execute tests. But that would limit our activities to dynamic testing only, omitting static testing. Sometimes people consider testing as verification of how a system corresponds to the given requirements. But it's wrong, because testing also includes another kind of check, called validation. It's how the system corresponds to the needs of business and users. Please check the glossary for full definitions of these two terms. So, what is testing? According to the ISTQB glossary, it's the process consisting of all lifecycle activities, both static and dynamic, concerned with planning, preparation, and evaluation of a component or system and related work products, to determine that they satisfied specified requirements, to demonstrate that they fit for purpose, and to detect defects. Let's talk about why we test. There can be many reasons for testing. These reasons are also called test objectives. They vary from project to project. To reach our test objectives, we may have to: Number 1. Evaluate documentation and code base using static testing techniques. Number 2. Verify if a product to be tested, also known as a test object, corresponds to these requirements. Number 3. Validate that a test object corresponds to the business needs and users' expectations. Number 4. Prevent defects using different techniques and approaches. 5. Find defects and failures. 6. Provide information about product conditions to the stakeholders. 7. Reduce risks related to software quality. 8. Check if regulatory requirements and standards have been met. Other two definitions that get mixed up quite often are testing and debugging, but they're different. We talked about testing a little bit earlier. Executing tests can show failures that are caused by defects in the software. Debugging, on the other hand, is the process of finding, analyzing, and removing the causes of failures in a component or a system. One more time, they are different. Let's see an example of how it works. In some cases, testers are responsible for the initial test and the final confirmation test, while developers do the debugging, associated component, and component integration testing. However, in agile development and in some other software development life cycles, testers may be involved in debugging and component testing. Here are a couple more terms that get confused. They are testing and quality assurance. While people often use the phrase quality assurance to refer to testing, these are not the same. We know what testing is. Let's talk about quality assurance for a second. Quality assurance consists of activities focused on providing confidence that the quality requirements will be fulfilled. In other words, it is typically focused on adherence to proper processes in order to provide confidence that the appropriate levels of quality will be achieved. When processes are carried out properly, the work products created by those processes are generally of higher quality, which contributes to defect prevention. In addition, the use of root cause analysis to detect and remove the causes of defects is important for effective quality assurance. Quality management, which includes all activities that direct and control an organization with regard to quality, ties QA and testing together. And then there is quality control. It involves various activities, including test activities, that support the achievement of appropriate levels of quality. Terms like errors, defects, and failures are usually synonymous in our everyday speech. But when it comes to software testing, it is necessary to distinguish between them. Let's review them as a chain of events. A person can make an error, which can lead to the introduction of a defect, also known as a bug, in the software code. If a defect is executed, it may cause a failure of a system. So, in other words, a human action that produces an incorrect result or an error can lead to an imperfection or deficiency in a work product where it does not meet the requirements or specifications. That's a defect, which may cause an event in which a component or system does not perform a required function within the specified limits. That's a failure. So, for example, you get distracted and make a mistake while coding. Again, that's an error. As a result, your code calls for a monthly report where it should be calling for a daily report. That's a defect. When the script is executed, it generates a monthly report, which was not what the specification required. That's a failure. The saying goes, to err is human, to forgive divine. Unfortunately, there is no divine component in software testing. It is quite unforgiving. Here's an example of a programming error with catastrophic consequences, the so-called 2010 flash crash. It happened on the 6th of May 2010, lasted for about 36 minutes, and, during the collapse stage, caused the loss of $1 trillion for the US stock market. The event was caused by a number of factors, and one of them was a faulty cell algorithm that disregarded the prices while only taking the volume information into account. Considering the speed at which the modern exchanges work today, it took minutes for this buy-sell cycle to hurt the world's economy. One of the important questions about software defects we need to ask ourselves is, when do they arise? This picture displays 4 possible scenarios. In the first case, everything was done right at every stage of the life cycle. This is the best case scenario, but not a very realistic one. Besides, this scenario contradicts the testing principles we are going to go over later in this video. The absence of bugs is deceptive, and even though you don't see them, it doesn't mean that the software is defect-free. In the second case, the requirement and design stages went well, but some defects were introduced at the development stage. These bugs need to be discovered through testing and then get resolved. This is a more lifelike scenario which testers encounter on a daily basis. Third scenario. Mistakes are made at the design stage. If they are not found and closed, the product will have design flaws, still correctable, but at a higher cost. Finally, in the worst-case scenario, the mistakes are made on the stage of writing the requirements and reproduced from there on, snowballing until the product is released. As a rule, such mistakes are the most expensive ones. The root causes of defects are the earliest actions or conditions that contribute to the creation of the defect. In other words, they're the sources of a defect such that if it is removed, the occurrence of a defect is decreased or removed. Defects can be analyzed to identify their root causes, so as to reduce the occurrence of similar defects in the future. By focusing on the most significant ones, we may reach the process improvements that prevent a significant number of future defects from being introduced. It might seem a bit illogical that software has defects. After all, every party involved loves quality and hates bugs. Nobody wants mistakes in the code, and yet they still come up. Why? The reasons are too many to mention. One of the biggest causes is a failure to communicate. The lack of clarity between different project stakeholders, botched or misrepresented requirements, and cognitive biases introduce mistakes, leading to defects which end up causing failures. Time constraints are another crucial factor. Project scheduling is often done based on incorrect assumptions. Impending deadlines bring pressure, loss of concentration, and mistakes. Automation, or the lack of thereof, is another contributor. Sometimes we don't have the resources to implement automation in order to achieve the required coverage. Or it can be the other way around. Instead of running a manual test that only takes 5 minutes, you spend 5 hours automating it and still make a mistake. And the list goes on. So rigorous testing is necessary to discover the bugs and increase the quality of the system. This is measured in terms of the number of defects found, the amount of tests run, and the extent to which the system is covered by tests. We can do this for both the functional software attributes, for example, sending and receiving an order correctly, and for the non-functional ones, for example, sending and receiving an order quickly. Let's talk about 7 testing principles. Principle number 1. Testing can show that defects are present, but cannot prove their absence. Testing reduces the amount of undiscovered defects remaining in the software, but even if no bugs are present, it doesn't prove the app is perfect. The absence of proof is not the proof of absence. The fact that you gaze into the night sky and see no exoplanets doesn't mean that they are not there. We have been looking for Earth-like planets for a very long time, but it wasn't until 1995 that we found one. The same goes for the search for Planet 9 in our solar system. We haven't found it yet, but it doesn't mean that it's not out there. Testing is aimed at proving that software contains defects, rather than proving that it doesn't. Confirming that it doesn't is impossible anyway. Principle number 2. Exhaustive testing is impossible. It means testing all combinations of inputs is not feasible, except for trivial cases. Instead of exhaustive testing, it is recommended to focus the efforts on risks and priorities. Even with the simplest program that requires entering a number into a field, the amount of all possible test case combinations can become infinite. And the test case is not just one variable. It's a set of preconditions, inputs, actions, expected results, and postconditions developed based on test conditions. Now imagine that we're testing a complex exchange platform. Add the limitation applied by time and budget, and you will see why the best practices suggest targeting the most important test cases. Principle 3. Early testing. Testing activities should start as early as possible in the software development lifecycle and should be concentrated on predefined objectives. The reason for that is very simple, and we cannot stress its importance enough. The earlier we find a defect, the cheaper it is to fix it. Besides, a defect discovered at the requirement stage is much easier to fix than the one found during the acceptance testing, when each component may affect the other ones in an unpredictable way. As you go from stage to stage, the cost of fixing a bug grows exponentially. Principle 4. Defect clustering. A small number of modules contain most of the defects found. According to the 80-20 Pareto principles, 80% of defects are usually found in 20% of the source code. The explanation for this effect can lie in the fact that some parts of the system are more complex than the others, or written according to the lower quality specifications. What it means to a tester is that if a bug is found in a certain part of the system, then chances are there will be more of them hiding nearby. Principle 5. The pesticide paradox. If the same tests are repeated over and over again, then sooner or later they will no longer find any new bugs. Let's just say the bugs that survive the most intensive testing routine become in some way immune to this test set. It is similar to bacteria becoming resistant to certain type of antibiotics if they are used repeatedly. Testing in order with the same parameters may be successful at first, but repeating it over and over again will soon stop bringing any results and give us a false sense of absence of defects. But try changing one parameter and it will probably uncover new bugs. To overcome the pesticide paradox, the test cases need to be regularly revised and new ones need to be written. Principle 6. Testing depends on the context. Testing is diverse and context-dependent. For example, safety-critical software is tested differently from an e-commerce site. Take Google, for example. They can afford to release an under-tested product and let their users do their work for them. But what could be acceptable for Google is hardly acceptable for software powering medical equipment or spaceships. This is a completely different level of accountability. The stock exchange software lies in between. It will not kill anyone if not tested thoroughly enough, but it can hurt investments, jobs, and economic stability. Principle 7. Absence of errors is deceptive. Finding and fixing defects does not help if the system we've built is unusable and does not fulfill the needs and expectations. If the system does not do what the user wants from it, the absence of defects is pointless. Now, let's talk about the test process, which is the set of interrelated activities consisting of test planning, test monitoring and control, test analysis, test design, test implementation, test execution, and test completion. One thing you have to understand is that there is no universal way to organize it. But there are several sets of testing activities which can help you to achieve objectives better. Keep in mind that in every situation, context is important. Contextual factors that influence the test process for an organization include, but not limited to: 1. Software development lifecycle model and project methodologies. 2. Test levels and test types. 3. Product and project risks. 4. Business domain. 5. Operational aspects, for example, budget and deadlines. 6. Organizational policies and practices. And 7. Required internal and external standards. Now that we know what affects the test process, let's look at all the stages that it consists of. Let's do it one more time. So these stages are test planning, test monitoring and control, test analysis, test design, test implementation, test execution, and test completion. Test planning involves the activities that define the objectives of testing and the approach for meeting test objectives within the constraints imposed by the context. Test plans may be revisited based on the feedback from monitoring and control activities. It is worth mentioning that it would be very useful if the test basis has measurable coverage criteria defined. The coverage criteria can act effectively as key performance indicators, KPIs, to drive the activities that demonstrate achievements of software test objectives. Test monitoring involves the ongoing comparison of actual progress against the planned progress, using any test monitoring metrics defined in a test plan. Test control involves taking actions necessary to meet the test plan objectives. During test analysis, the test basis is analyzed to identify testable features and define associated test conditions. In other words, test analysis determines what to test. During test design, the test conditions are transformed into high-level test cases, sets of high-level test cases, and other testware. So test design answers the question of how to test. Test data serves to assign concrete values to the inputs and expected results of test cases. Such concrete values, together with explicit directions about the use of the concrete values, turn high-level test cases into executable low-level test cases. The same high-level test case may use different data when executed on different releases of the test object. The concrete expected results which are associated with concrete test data are identified by using a test oracle. During test implementation, the testware necessary for test execution is created and/or completed, including sequencing the test cases into test procedures. So, test implementation answers the question of, do we now have everything in place to run the tests? During test execution, test suites are run in accordance with the test execution schedule. Test completion activities collect data from completed test activities to consolidate experience, testware, and any other relevant information. Test work products are created as the part of test process. Just as there is significant variation in the way that organizations implement test processes, there is also significant variation in the types of work products created during the process, in the ways those work products are organized and managed, and in the names used for these work products. Let's look at those test work products by stage. During test planning stage, there are test plan, including test basis, and entry and exit criteria. During test monitoring and control stage, there are test summary and progress reports. During the test analysis stage, there are test conditions. During test design, there are high-level test cases, test data, environment configurations. During the test implementation, there are procedures, suites, and test execution schedules. During the test execution stage, there are TC statuses and defect reports. During the test completion stage, there are test summaries, reports, action items, CRs, finalized testware. One more time. Test work products and their names vary significantly, but regardless of these variations, in order to implement effective test monitoring and control, it is important to establish and maintain the degree to which a relationship can be established between two or more work products, which is called traceability. In addition to evaluation of test coverage, good traceability supports analyzing the impact of changes, making testing auditable, meeting IT governance criteria, improving the understandability of test progress reports and test summary reports to include the status of elements of the test basis, for example, requirements that passed their tests, requirements that failed their tests, and requirements that have pending tests. relating the technical aspects of testing to stakeholders in terms that they can understand, providing information to assess product quality, process capability, and project progress against business goals. Some test management tools provide test work product models that match part or all of the test work products outlined in this section. Some organizations build their own management systems to organize the work products and provide the information traceability they require. The mindset we want to adapt while testing is different from the one we use in the development. If our goal is to create something, we tend to work positively and constructively to solve problems and to deliver a product that meets specific need. However, when we test this product, we'll look for its flaws. Our attitude is critical and destructive. In this case, our goal is to prove that the product is short of expectations. Carl Sagan stated in his Rules of Skeptical Thinking that we should not cling to the hypothesis just because it's ours, and we should always get an independent confirmation. This is a common practice in scientific community. Suppose you are the head of the movie production team. You pick your actors and locations. You work on the storyline and you frame each shot carefully. You spend weeks pacing the cutting room floor. You add the soundtrack. The release date is here. Your movie is ready, but all of this doesn't mean that you have made a good one. For every Dark Knight, there is Batman and Robin. For every Matrix, there is Matrix Resurrections. The critics and the viewers have a different mentality than the production team, and they are not going to overlook the plot holes, bad acting, and poor taste. Same goes for software testing. Building software and testing software differ in the underlying logic. We do not mean that a tester cannot be a programmer or that a programmer cannot be a tester, although these are often separate roles. Sometimes a good director will be as objective about his own work as the critics. There are countless stories of movies going through extensive reshoots to get some of the finer points just right. So, with the right mindset, programmers can test their own code, and they can resolve many issues before anyone else sees the prototype. However, we all know it is difficult to find your own mistakes. So, all of them often rely on others to help to test their work. This other person might be a fellow analyst, designer, or developer. We can identify several degrees of separation between the person who wrote the code and the one who checks it. We organize them in a simplified progression. Tests can be run by the person who wrote the item on the test, another person within the same team, such as another programmer, a person from a different division of the same company, and finally, tests can be designed by a person from a different organization, such as a specialized technology vendor. Early in the lifecycle, requirement reviews by someone other than the author help find defects before coding starts and help build the right software. After coding is complete, the software can be tested by an external team. This separation avoids author bias and often more effective in finding defects and failures. We should note that independence is not necessarily the most important factor in high-quality testing. Developers can be self-critical and benefit from knowing their work. Some software development methodologies insist on developers designing tests before they start coding and executing those tests continuously as they progress. This approach encourages early testing, which is cost-effective. This practice is one of the key testing principles promoted by the ISTQB Foundation level syllabus. Testers and test managers need to have good interpersonal skills to be able to communicate effectively about defects in order to build positive relationships with their colleagues. Here are some ways to mitigate possible conflicts. Number 1. Start with collaboration rather than battles. Number 2. Emphasize the benefits of testing. Number 3. Communicate test results and other findings in a neutral, fact-focused way. Number 4. Try to understand how the other person feels and why he may react negatively. And number 5, confirm that the other person has understood what has been said and vice versa. This concludes the first chapter of the ISTQB Foundation level preparation course. Good luck with your studies, and I'll see you at chapter 2.